Good day, sir. So today, we will discuss the reactions of hydrocarbons containing preparation of acetylene, ethylene, reaction with potassium permanganate, and reaction with iodine. So buckle up and enjoy the ride as we dive deep into the wonders of hydrocarbons.
And so let us begin with the preparation for acetylene. I will discuss the preparation of acetylene, a hydrocarbon characterized by its triple bond, making it an alkyne. This process highlights the reactivity of alkynes and their generation in the lab. So these are the objectives for my discussion on the preparation of acetylene. So moving on to the schematic diagram of the procedure. The materials needed includes filtering flask, 5 grams of calcium carbide, and 100 ml of distilled water. So for the procedure, into a filtering flask, introduce around 5 grams of calcium carbide lamps and assemble the rest of the setup. Through the Tesla tube, carefully add 100 ml of distilled water. Let the acetylene displace the air in the flask first. Collect the glass in a vial filled and submerge in a water trough. Prepare 5 samples and label each vial properly. Moving on to the results and discussion. So during the reaction, bubbles are observed, indicating the evolution of acetylene gas. After the reaction, the solution appears turbid due to the formation of calcium hydroxide. Acetylene, a colorless and odorless gas, exhibits unique properties due to its triple bond. Its generation is supported by the chemical equation above, where calcium carbide reacts with water. The reaction is highly exothermic, ensuring efficient gas release. Next, reaction mechanism. The mechanism involves the nucleophilic attack of water on calcium carbide. Water donates protons, leading to the release of acetylene and calcium hydroxide precipitate. This showcases acetylene's unique ability to form silver acetylide when subjected to tests like ammoniacal silver nitrate, confirming its alkyne structure. So in conclusion, the preparation of acetylene highlights the practical application of hydrocarbon reactivity principles. The reaction serves as a foundation for studying alkynes and their chemical properties, particularly in synthetic and analytical chemistry. Thank you so much.
Now, I will discuss the preparation of ethylene, which is a fundamental unsaturated hydrocarbon in organic chemistry. The primary objective of this experiment is to discuss on how to prepare ethylene through a dehydration reaction of ethanol. To prepare ethylene, we will use ethanol, which will undergo dehydration in the presence of an acid catalyst, typically concentrated sulfuric acid or oxide, to eliminate molecules of water. This then leads to the formation of ethylene. During this reaction, the ethanol is heated in a test tube and we observe the formation of ethylene gas. This gas is then collected by displacement of water in water trough, and then the reaction continues as long as the heat is applied. As we heat the mixture, we start to see bubbles forming, indicating the production of ethylene gas. The gas can be tested by passing it through a solution of bromine water. Ethylene will decolorize the bromine, confirming its presence as an unsaturated compound. Now moving on to the results and discussion. If the bromine water turns colorless, it is confirmed that ethylene is indeed an unsaturated hydrocarbon. The reaction of ethylene with bromine is an addition reaction where bromine atoms add across the double bond of ethylene, resulting in dibromoethane. In conclusion, the preparation of ethylene through the dehydration of ethanol is a fundamental organic reaction. By using concentrated sulfuric acid as a catalyst, ethanol loses a water molecule, forming ethylene. This reaction demonstrates key concepts in organic chemistry, such as dehydration and the formation of unsaturated hydrocarbons. And that is all. Thank you. Potassium permanganate, or KMnO4, is a powerful oxidizing agent used to test for the presence of unsaturation in hydrocarbons. This reaction is significant because it helps us distinguish alkanes from alkenes and alkynes based on their reactivity. The objective of this experiment is to identify and distinguish between saturated and unsaturated hydrocarbons based on their reactivity with potassium permanganate. Specifically, the experiment aims to observe the oxidation reactions of hydrocarbons with KMNO4 and determine the presence of double or triple bonds through color changes and precipitate formation. Next is schematic diagram of the procedure. Materials needed: dilute potassium permanganate solution, test tubes, hydrocarbon samples, ethylene, acetylene, and cyclohexane, and dropper. For each procedure, a dilute or alkaline solution of KMNO4 is prepared, which has a deep purple color. Next, the hydrocarbon sample is added to the KMNO4 solution and mixed. Observations are made to detect color changes or the formation of precipitates. Alkanes and aromatic hydrocarbons are generally unreactive with KMNO4, so the purple color remains unchanged. Alkenes and alkynes are unsaturated hydrocarbons that are oxidized by KMNO4. Alkenes are converted to geminal diols, while alkynes form geminal diketones. Positive result is marked by the disappearance of the purple KMNO4 color, the formation of a brown precipitate of manganese dioxide or MnO2 indicating oxidation. Now let's discuss the results and reaction mechanism. For ethylene, which is an alkene, observation is the purple solution of KMNO4 turned brown and precipitate of MnO2 is formed. The mechanism is the double bond in ethylene is oxidized to form a geminal diol. Next is acetylene or alkyne. Observation is the purple color disappeared and a brown precipitate is formed. Mechanism is the triple bond is oxidized, forming a geminal diketone as the product. Next is the cyclohexane or an alkane. No reaction occurred, the purple color remained unchanged. Alkenes lack double or triple bonds and are thus unreactive with KMNO4. Ethylene and acetylene both decolorize the KMNO4 solution and form a brown precipitate. Cyclohexane did not react, confirming it is saturated. In conclusion, the Bayer's test with potassium permanganate successfully distinguished between saturated and unsaturated hydrocarbons. Unsaturated hydrocarbons like ethylene and acetylene reacted, resulting in the decolorization of the purple solution and the formation of a brown precipitate. In contrast, saturated hydrocarbons like cyclohexane showed no reaction. These results confirm the presence of double and triple bonds in alkenes and alkynes, respectively, and demonstrate the utility of KMNO4 as a reagent for identifying unsaturation in hydrocarbons.
Now, let us proceed with the reaction of iodine. These are the objectives of this experiment. Now, iodine reacts with hydrocarbons through various mechanisms. Alkanes undergo free radical substitution, replacing hydrogen ions with iodine. For example, methane plus iodine yields methyl iodide and hydrogen iodide. Alkenes undergo electrophilic addition, forming vicinal diiodides. Ethene plus iodine produces 1,2-diiodoethane. Reaction conditions such as temperature, pressure, solvent, and light influence the outcome. Next is the schematic diagram of the procedure. The materials needed are test tubes or vials, 2 for each hydrocarbon. Hydrocarbon samples such as LPG, ethylene, acetylene, hexane, cyclohexane, and toluene. Next is the iodine in carbon tetrachloride solution. Carbon paper or aluminum foil, syringe, distilled water, and blue litmus paper. Now before we proceed to the procedure, let us remember that the color of the reagent, which is the iodine in carbon tetrachloride, is purple. Now first, prepare 2 test tubes or vials for each hydrocarbon sample. Wrap 1 test tube or vial with carbon paper or aluminum foil to block light, and leave the other uncovered. For the liquid hydrocarbon, add approximately 0.5 ml of iodine in carbon tetrachloride solution to the wrapped and unwrapped tubes. For gaseous hydrocarbons like LPG, use a syringe to inject about 0.5 ml of iodine solution into the wrapped and unwrapped vials. Gently shake both wrapped and unwrapped samples every few minutes for 20 minutes. After 20 minutes, remove the wrap from the tubes or vials and observe any color changes. If the mixture in the vial is colorless, add around 1 ml of distilled water and shake to mix. Allow the layers to separate and dip one end of a glass rod into the aqueous layer. Touch the wet end to blue litmus paper and record observations. Now for the observations, take note that the positive results has color changes. If a hydrocarbon reacts with iodine, the solution may change from purple due to dissolved iodine to colorless or lighter in color, indicating that iodine has reacted with hydrocarbon. Formation of products. For alkenes like ethylene and acetylene, a positive result would involve the formation of iodo derivatives, which may be indicated by a color change. Now for the negative results, there are no reaction. If no significant reaction occurs, the solution remains purple, indicating that iodine is still present and has not reacted with the hydrocarbon. Now for the LPG, both wrapped and unwrapped samples remain colorless, indicating no significant reaction with iodine. Ethylene. The wrapped sample may show purple coloration due to iodine presence, while the unwrapped may turn colorless as it reacts with light to form products. Acetylene. Similar behavior to ethylene, purple in darkness but may become colorless under light exposure due to reaction. Now hexane and cyclohexane remain colorless in both conditions, indicating minimal reactivity with iodine. Last is the toluene. The wrapped sample may show purple coloration due to unreacted iodine, while light exposure could lead to a color change as it forms iodo derivatives. Now, let us proceed to the litmus test results. In all cases where mixtures were colorless after adding distilled water, litmus paper remained neutral, indicating that no acidic products were formed during the reactions. To conclude, this experiment highlights how different hydrocarbons react with iodine under varying light conditions. Alkenes and alkynes, like ethylene and acetylene respectively, react readily with iodine, while alkanes, like hexane and cyclohexane, show little to no reactivity. The use of litmus paper confirms that no acidic byproducts are formed during these reactions. Thank you.
I am Chino Mariel P. Daos.
I am Janine Tungal.
I am Liren Scaro.
I am Wilgin Ermac, and this has been Group 1 signing out.